So to make things simpler with thin film interference, it's really key that we understand there's only actually 4 possible things that they can ask you. Okay, there's 4 ways they can ask the question, and all it comes down to is the refractive index in the 3 media, and whether they want constructive or destructive interference at the end. So if I had an example where we have a wavelength of say 600 nanometers, and we want an anti-reflective coating on a lens, for example. So an anti-reflective coating would mean that we would want destructive. Now, we're going to squash everything. In reality, we're just having rays coming in at 90 degrees, passing through and reflecting outwards. We're going to represent it on this diagram, and we're going to represent the incoming ray here, the first reflected ray, the transmitted ray, the ray reflected off the second boundary, and the refracted ray back into the original medium. We can have additional media down here, but the questions that we have in IB are only relating to between 2 boundaries. Okay. In this question, I've said we've got 900 nanometers more. Destructive because it's an anti-reflective coating. We would then assume that air has a refractive index of 1, and I'm just going to make up some numbers. We say maybe the refractive index of the coating is 1.5, and the refractive index of the glass on the lens, maybe we're going to say is 1.9, okay, compared to air. So what I'm going to do is I'm going to look at my diagram, and I'm going to label the angles that I want. I'm going to say that my ray coming in has reached 0 degrees. Okay, it is starting on the upwards of the sine curve. And here we have a higher refractive index, so the reflected ray here would be 180 degrees. All cases, we're going from air to a more refractive index. In this case, because I want a destructive interference, because I want an anti-reflective coating, I need my second ray to exit with a phase of 360 degrees. As the ray passes through this boundary, I get to a second point of reflection. Can you see here that the boundary has a higher refractive index on the glass compared to the film? So again, we're going to have a change in phase of 180 degrees here. So what I need to do is work out what I need to add to this 180 to get to this 360. So I've got a ray coming in and a ray coming out. I need to add 180 degrees. Therefore, I need to have 90 degrees of phase, or 1/4 of a wavelength here, in order to be at 270 degrees through my sine wave when it leaves this boundary. And then I can have another 1/4 of a wavelength to get back to the 360 degrees that I need. In this case here, my thickness is going to be 1/4 of the wavelength. So all I need to do is work out what the wavelength is in this medium and find 1/4 of it. So as an example, 1/4 of the wavelength in air is going to be 150 nanometers. So my thickness here will be 150 divided by 1.5 is going to be 100 nanometers thick. So in order to find the thickness of my coating, I'm literally dividing 1/4 of a wavelength by the refractive index. And in this way, I don't need to use any formulas at all. And I'm always going to get the right answer, because the 2 formulas in the book, you don't know which case you're getting. Let's take another example. So I'm going to keep this the same. I'm going to have a boundary of air. I'm going to have my coating is at 1.5, and I'm going to have my more dense, optically dense boundary here. In ray, transmitted, second reflected ray. And in this case, I'm going to say that I want constructive. interference. In this case, I'm going to have 0 degrees starting 180 because I've got a more dense boundary. But in this case, I want 180 degrees phase in order for the two rays leaving to be in phase for completely constructive interference. Okay, so in this case, I still have a phase change here. I'm still going to have a change of 180 degrees. So if I start at 180 and I finish at 180, I need in total 360 degrees change in addition to the 180 to get back to my 180 degrees. So here I'm at 0 degrees. I want a half a wavelength in order to get to 180 degrees. I have 180 degrees phase change. I'm at 360 degrees. And then I have another half of a wavelength to get back to 360. I'm going to be at 180 degrees by the time I get here. Yes, I have my constructive interference. In this case, my thickness is going to be half a wavelength. And in order to find the thickness, I just divide that by my refractive index by the 1.5. That gives me the minimum thickness of the film. Again, we can always add multiples of half wavelengths and we get back to the same position. Let's have a look at the other one. Say I have a soap bubble and my soap has a refractive index of 1.3. My refractive index in air is 1 and my refractive index of air inside the bubble is 1. In this case, maybe I want constructive interference. So again, I'm starting here at 0 degrees, 180 here. I want 180 degrees here. Here, I'm not going to have any phase change because the refractive index is less. So I need 180 degrees of change. 180 degrees is half a wavelength. So I'm going to have a quarter of a wavelength here and a quarter of a wavelength here. In order to get to 90 degrees here, there's no change. So 90 here, I'm back to my 180. I get my constructive interference. My thickness here is a quarter of the wavelength, not quarter of a lambda, quarter of a wavelength here. In order to find the thickness, I divide a quarter of the wavelength of whatever the wavelength was in air by the 1.3. I've got my answer. The final situation, again, I'm going to do a soap bubble. It's going to be n is 1, n is 1.3, n is 1. Okay, in this case, we're asking for destructive interference. We're going to label the direction of my rays again. My input ray is still 0 degrees. I've got a more dense medium, so I will have a phase change at this boundary. It's going to be at 180 degrees here. If I look at the ray that passes through down here and comes out, I want destructive interference, so I need to have 360 degrees of change there. In this case, I'm not going to have any change of phase at this boundary because this is less dense than the medium that it was traveling in. So I need to get from 0 to 360 degrees through the film. 360 degrees is a complete wavelength, so I need half a wavelength here and half a wavelength here. That will give me 180 degrees in. There'll be no change. 180 degrees out, add 180 degrees, and back to my 360. I've got my destructive interference. My thickness here is going to be half of a wavelength in air over my refractive index. Gives our answer. And then we don't need to use any of the formulas at all. Just use the logic, draw the diagrams every time, and you should be fine.